Swayam Prabha. Digital India. Educated India.
This is lecture number 7. Hello everyone, welcome back. In the last class we started the review of the basic thermodynamics and we went through the first law and the second law of thermodynamics very briefly, okay, and it is expected that you already have some background. I am only covering the essential part which is necessary for understanding the energy equation for the compressible flows. Okay. So, using the first law and second law and considering that flow is isentropic, we derived some relations, and one of the relation was that this S 2 minus S 1 okay, will be equal to C p ln T 2 by T 1 minus R ln P 2 by P 1. Okay. So, we said that for a calorically perfect gas S depends on both the temperature and the pressure, right. So, if the flow is isentropic, okay, then S 2 minus S 1 will be equal to 0. Okay. So, in that particular case you can write this C p ln T 2 by T 1 minus R ln P 2 by P 1 equal to 0. Okay. And then you can manipulate it, this is ln T 2 by T 1 will be equal to R by C p, okay, or you can do it another way, ln P 2 by P 1 will be equal to C p by R ln T 2 by T 1, right. So, that means P 2 by P 1 your P 2 by P 1 will be equal to T 2 by T 1 to the power C p by R. Now, recall we had discussed C p equal to gamma R by gamma minus 1, therefore, C p by R will be equal to gamma by gamma minus 1, right. So, then P 2 by P 1 will be equal to T 2 by T 1 to the power gamma by gamma minus 1, right. So, we got the relation of pressure with temperature or the change in pressure with the change in temperature for an isentropic process, right. Similarly, if you use the other relation, okay, do you remember what relation was between the temperature and the volume? Okay. So, the relation was C p ln T 2 by T 1 plus R ln V 2 by V 1 equal to 0. Okay. Once again, this is the specific volume. Okay. This is the symbol that I am using for specific volume. Okay. So, if you use this relation here, okay, you can, this will be C v. Okay. C v ln T 2 by T 1. Okay. So, you can have do this C v by R also. So, ln V 2 by V 1 would be minus C v by R ln T 2 by T 1. Okay. So, this gives you V 2 by V 1 is equal to T 2 by P 1 T 1 to the power minus C v by R, right. Recall C v equal to R by gamma minus 1. Therefore, V 2 by V 1 is equal to, this will be T 2 by T 1 to the power minus 1 by gamma minus 1, right. So, we got two relation, okay. One is the pressure with temperature, okay. The other is the volume with temperature. Okay. Now, you can combine both these relations, okay, and if you combine both these relations, right. So, you had P2 by P1 is equal to T2 by T1 to the power gamma by gamma minus 1, and V2 by V1 was equal to T2 by T1 to the power minus 1 by gamma minus 1, which can be written as V1 by V2 will be T2 by T1 to the power 1 by gamma minus 1. So, this is 1, this is 2, right. So, combining 1 and 2, 1 and 2, you can write P2 by P1 would be V1 to the power B to the power gamma, right. If you take a power of gamma of 2, you will get this T2 by T1 power to power gamma minus 1, which will be like this, and that will be because V1 is inversely related to the density. So, this will be rho 2 by rho 1 to the power gamma, and that is nothing but T2 by T1 to the power gamma by gamma minus 1. Okay. So, this is a very useful relation. Okay. And the way to remember it, I mean you can recall it, but very simple thing that you have remembered in our maybe the school days or the college days is because P V to the power gamma is equal to constant. Okay, it can be written as K, or P by rho to the power gamma is equal to constant, okay, for an isentropic process, right. So, next, now that we know that, okay, let us find out some of the things that we already know. Okay. One is the speed of sound. Okay. So, what is the speed of sound? So, when we speak, okay, so waves travel, and you can basically find out at what speed the wave is traveling. You can basically consider a system on the left of the wave, on the right of the wave, and use this mass conservation and the momentum conservation. In this case, it is the x momentum conservation, and you can basically come to this relation, which is well known relation, okay, which is square root of dP by d rho at constant entropy. Okay. This is the relation that we will get. So, you will consider basically change in the density and the pressure due to the wave, okay, and use the mass conservation, and you will get this relation. Okay. This is also something that you have studied earlier. Okay. So, for if the system is isentropic, okay. So, before going there, okay, so A is equal to, so A square will be dP by d rho at constant entropy, and earlier we have seen that tau s equal to 1 by rho dP by d rho at constant entropy. Okay. So, this A square or your tau s can be written as 1 by rho A square. Okay. So, your speed of sound can be expressed in terms of the compressibility of the system. Okay. So, if the system is more compressible, okay, so A square will be 1 by rho tau s. Okay. So, system has higher isentropic compressibility, you will have lower speed of sound. Okay. So, now going forward, how do we determine this tau s or A square, right. So, we know that the tau s is what, dP by d rho s, sorry, d rho by dP, not dP by d rho. Okay, that is why there is a problem here. This is d rho by dP. So, here it will be change in density per unit per change in pressure, okay, and this is dP by d rho. Okay, this is d rho by dP. Okay. So, this is d rho by dP to the power s. Okay. tau s is 1 by rho d rho by dP at constant entropy, or minus 1 by V dV by dP constant entropy, right. Now, how do we get d rho by dP at constant entropy? So, we use the isentropic relation. So, for an isentropic process, you know the relation that we just derived, P v to the power gamma equal to constant. I am using k for the constant, and which is equal to P by rho to the power gamma, right. So, P will become k rho to the power gamma. Okay. I think there is a typo here. This is k rho to the power gamma. Okay. So, now we want to find out dP by d rho. First find the dP by d rho, and then you can find the d rho by dP, right. So, that will become k gamma rho to the power gamma minus 1, right. Now, but we know that k equal to p rho to the power gamma. So, you can use the same relation. Okay, this is k will be p by rho to the power gamma rho to the power gamma minus 1, right. This will get cancelled and this will become 1. So, this is nothing but gamma p by rho. So, del p by del rho is equal to gamma p by rho, right. So, at constant entropy, of course. So, a speed of sound will be a square equal to square root of gamma p by rho, and if you use our relation, the ideal gas equation, this will become square root of gamma r t, right. So, if you know the temperature, you can find out what is your speed of sound. Okay. For a given gas, if you know the temperature, and you can find the speed of sound, and that is why let us say, sorry, this is a not a square, this is a square will be gamma p by rho, right. So, if you are so as you go up in the altitude, okay, so let us say this is your sea level. So, you have got certain temperature here, okay, and as you go up, your temperature decreases. Okay. So, there is some linear relation that every some meter 100 meters or so, you have some decrease in temperature. So, your this is let us say your T 2 and this is your T 1 or this is T 0. Okay. So, this will be T 2 less than T 0. So, as you go in the height, your temperature basically decreases, and that is why your speed of sound decreases. Okay. I will relate it to the Mach number when we when we discuss the Mach number in the few slides. Okay. So, this is one thing. Secondly, you can also use this for the isentropic entropy. Okay. So, remember tau s was 1 by rho d rho by d p at constant entropy, okay, and that we saw that this dP by d rho at constant entropy by was what gamma p by rho. That's gamma p by rho, right. So, this will be rho by gamma p here, rho will cancel out. So, your compressibility at constant entropy will be 1 by gamma p, right. Recall your isothermal compressibility by 1 by p, right. So, if you take the ratio of tau s by tau t, that will be 1 by gamma, right. So, your isentropic compressibility is even smaller than your isothermal compressibility, because gamma is higher than 1, right. Remember, gamma is equal to n plus 2 by n, right. So, it is greater than 1. So, for monatomic it is 5 by 3, for diatomic it is 7 by 5, triatomic it is 9 by 7, right. So, if you go back to our earlier problem, that find out isentropic compressibility for or at 1 atmosphere, okay, for air at medium which is 1 atmosphere, pressure 1 atmosphere. So, if you use that, so tau s will become 1 by gamma p, and let us say if it is at air. So, that will become 1.4 and pressure will be 10 per 5, around 10 per 5. Okay. So, that is so this will be smaller than your thermal compressibility, but it will be around the same range, which is like 10 power minus 5, little bit smaller than that, okay, meter square per Newton. So, this is the value that you are going to get for the isentropic compressibility. So, both are very comparable, except that the isentropic compressibility is slightly lower than the tau t. Okay. Now, comes to the concept of the Mach number, and you cannot basically deal with a compressive flow without defining the Mach number, and the Mach number has been given by Professor Ernest Mach, okay, who basically gave this number and also basically visualize some of the shocks that form at supersonic conditions. Okay. So, the Mach number is basically a number which relates your flow velocity to the speed of sound, right, m equal to u by a, right. So, why it is very important is because let us say if you have an object, it may be an aircraft, okay, or it may be missile or whatever it is moving at a certain speed. So, as it moves, okay, it creates wave, okay, which travel, right. So, if the object is moving and object is moving at a lower speed, okay, and the waves are moving at a higher speed, that means this u is less than a. Okay. So, the object is moving at lower speed, but lower speed than the speed of sound, right. So, u is less than a. So, then in that case Mach number is less than 1. Okay. So, in that case this kind of flows are called the subsonic flows, where the object is moving at a speed lower than the speed of sound. On the other hand, you might have a situation where the object is moving at the same speed as the speed of sound. Okay. In that case, as the object is moving, the waves which are forming due to the movement of the object are basically moving along with the object. In that case, u is equal to a, okay, and this is equal situation which is Mach equal to 1, and this is called the sonic flow. Okay. Now, third is a very interesting situation where the object is moving at a higher speed than the speed of sound. Okay. So, what are the consequences of that? Okay. So, if the before basically the sound, if let us say let us talk about the same object, okay, here, okay, let's say this is the object that is moving this direction at a speed which is higher than the speed of sound, right. So, the waves that are forming here, okay. So, before basically this wave can go out, you can basically object has moved forward, and because the object has moved forward, okay, there will be region which will be basically the zone where it will affect the flow, and there will be zone which is outside of this where it will you will not know the object has moved also, right, because the object is moving very fast, right. So, in this case those who are in this region, okay, because this pressure waves are basically confined in this region, okay, you can have lines like this. Okay. So, everyone who is in this region, if you are standing in this region, okay, you will find out that the object has moved, but if you are standing in this region, you have no information that object is coming, because the waves have not reached here, right. So, in this case, because there is a flow outside and the flow had to adjust to the body, right, because the body is suddenly felt there, right. In that case, what will happen, that you may experience a shock, okay, this region here. Okay. So, you might experience a shock, and this has got very interesting phenomena when the Mach number is. So, in this case is Mach greater than 1, right. So, in this case u is greater than a. So, Mach is greater than 1 and this situation is called the supersonic. Okay. And the things change drastically in this kind of situation. Okay. In fact, the very simple relation that you know, the area velocity relation. So, let us say you are holding a water pipe in your garden, and if you press the water pipe, what will happen? Your flow speed increases, right. So, as you decrease the area, the speed of the flow is increasing. The reverse thing will happen in the supersonic flow, which sounds very counterintuitive, that if you decrease the area, okay, your speed will also decrease. Okay. And I mean, that is not the subject of this course, and you will read it about in gas dynamics, but just to know that this is a very important thing, that as you decrease the velocity, decrease the area, the velocity also decreases, and that is called the area velocity relation. Similarly, if you increase the velocity, increase the area, your speed will also increase. Okay. And that is how your the CD nozzle is designed. Okay. So, the flow here is, let us say this is your subsonic flow, and you design in such a way, let us say this is Mach number less than 1. Now, the area is decreasing. So, in this region if you see, the area is decreasing, okay, and this is called the throat, which is the region of the minimum area. Okay. So, speed has decreased, and it can, because speed is area is decreasing, the Mach number will increase, because this is a subsonic region, and then it can go to this region which is Mach equal to 1. Now, in this region what is happening? In this region the area is increasing, right, but the flow now here is supersonic, right. So, in this case the behavior will be exactly opposite to what we had in the subsonic flow. So, despite the area is increasing, the Mach number will also increase in this case, okay, and that is how you get basically the supersonic flow, okay, in a CD nozzle. This is called a CD nozzle, okay, convergent divergent nozzle or de Laval nozzle. Okay. So, this kind of equipment is used to get a supersonic flow. Okay. So, we got the subsonic regime, the sonic regime, supersonic regime. You can also have a hypersonic regime, where the Mach number is much higher than 1, okay, maybe let us say Mach equal to Mach greater than 5. Okay. And in this kind of cases, you may get ions, your molecules may dissociate, okay, some new molecules may form. So, in ionization and dissociation becomes important, and there are so many effects that will come, because you will have very thin shock layer, okay, in this case of these flows, and these kind of flows are, because of these things, these are called, kept in a separate category, which is basically the hypersonic flow. Okay. In this case, not only the aerodynamics, but the thermodynamics also become very important. Okay. And in fact, what we have been saying earlier, that the perfect gas equation may not be valid in this, because that will be you will have the reacting flows in this particular case. Okay. And one last situation is when you have the Mach number between 0.8 to 1.2, okay, somewhere in this region. So, this is called a transonic flow. Okay. And why it is called a transonic flow? Because, so this Mach number that I am talking about is what is the free stream Mach number, okay, but you can also have the local Mach number, where you can take the local velocity and local speed of sound. So, let us say if you have a wing or an aerofoil, and you started with a Mach number which is 0.8. Okay. So, it so happen because the flow accelerates here, okay, and at certain point of time it may reach the Mach number, which is basically let us say equal to 1, and then you can get a shock here. Okay. So, it is not compulsory, but it may happen if the flow reaches to Mach 1. So, in those kind of cases, despite your free stream Mach number to being less than 0.8, you might get a shock. So, that is why these kind of situations are kept in a separate category, which is called the transonic flow. Okay. Similarly, if you go to the higher Mach number, let us say 1.2, you can get a shock which is in front of the body as well as in the back of the body. Okay. So, this was a slight detour because I wanted you to introduce to the concept of Mach number. Now, the final thought that I want to give before I conclude today's class is that see, the Mach number depends on both the velocity and the speed of sound, okay, u by a. Now, speed of sound changes with the altitude, right. So, despite an aircraft being at the same speed at the ground as well as let us say an altitude of 12 kilometer, okay, the Mach number will be different. We discussed about the subsonic condition, supersonic condition, hypersonic condition, and even the transonic condition. So, transonic condition is when the Mach number is between 0.8 to 1.2. So, in that case, despite the free stream Mach number to be less than 1, you can have the situation where you can get a shock on the body, okay, because the flow will accelerate on the body and you might get a shock. Okay. So, we will just finish with one last thought, and that is basically that despite having going with the same speed, okay, at the ground level and at higher level, your Mach number may be different. And there is a question regarding that, I mean related to that, which is put here, and this will be one of your assignment questions, is that an aircraft flies at a constant Mach number irrespective of its altitude. That means, let us say this is an aircraft here, this is at sea level, okay, and at certain other level, okay, here, which is at 12 kilometer, okay, but the Mach number remains the same. So, if I call it Mach 0 and Mach 1, okay. So, the Mach 0 is sorry, this at sea level condition it flies at 127 kilometer per hour faster than an altitude at 12 kilometer, right. So, if the velocity here is my u1, this will be basically u0 is equal to u1 plus 127 kilometer per hour. You can basically convert it to meter per second. So, the question is what is the Mach number of aircraft, right. You can use the table, okay, the atmospheric table. So, that will give you the how temperature varies with the altitude with height. So, you know the temperature here T0, you know the value of temperature at height 12 kilometer, which is T1, right. You can calculate speed of sound, A1 is equal to square root of gamma at T1, okay, and here you can calculate the value A0, which is square root of gamma T2, right. Now, it says that aircraft flies at a constant Mach number, right. So, that means your M1 equal to M0, right. So, that means your u1 by square root of gamma r T1 will be u1 plus 127 kilometer per hour divided by square root of gamma r T2, right, because the Mach number remains the same. You can make the calculation, and because you know the value of T1 and T2 from the atmospheric table, you can calculate the value of u1, and from that you can calculate the value of Mach number. Okay. So, remember that as you go above the ground, your speed of sound decreases. So, if an object is flying at the same speed at the at a certain height as it was in sea level, the Mach number will increase as you go up, but right. Okay. So, with that we will stop for the class today, and I just want to end with a thought, and we will get back to the relation between the Mach number and your change in pressure, which is related to change in density, right. So, you might have studied in your classes that if Mach number is less than 0.3, which is the free stream Mach number, then flow is incompressible. Flow can be considered incompressible, right. How do we get this number 0.3, and what happens? How do you ensure that below 0.3 your change in density is less than 5%, because that is the definition of compressibility that we have been following. Okay. If the change in density is more than 5%, we can no longer consider the flow to be incompressible. Remember, there is no flow which is truly incompressible. Okay. So, we will get a relation when we go to this momentum conservation equation, Okay, we will get the Euler equation and we will find the relation between change in pressure and change in Mach number, and we know that the change is related to the change in density with a factor which is the compressibility. Okay. And we will see that as the flow speed increases, as the Mach number increases, flow becomes more and more compressible. So, for compressible flows, the two criterion, the medium should be compressible, which we meet when we go from liquid to air. Okay. But the other thing is that Mach number should also be sufficiently high. That means that if let us say Mach number is let us say 0.01, it is a very low Mach number. Okay. That means the speed is very small compared to the speed of sound. In those cases, your change in density will be very small, and you can safely treat those flows as an incompressible flow, and it will not make a difference whether you perform the flow in using a compressible solver or an incompressible solver. In fact, if you try to solve this flow is very small Mach number in a compressible solver, it will take much longer time because your time step will be very small. Okay, and it is a good idea to use a incompressible solver if the Mach number is very low. And for any flow, I mean most of the flow where the Mach number is let us say less than 0.1 or so, the difference between a results coming from a compressible code and an incompressible code will be very minimal. Okay, and at least it will not affect the dynamics. Okay, with that we will stop here. Thank you very much.